Welcome to the presentation on polytropic process applied to a closed system based on first law of thermodynamics. Any thermodynamic process can be expressed in terms of a polytropic process, that is PV power n is equal to constant. The n is called as polytropic index. The n value can be changed from 0 to infinity. For example, if the n is equal to 0, it is called as constant pressure process, that is isobaric process. Or finally, if n is equal to infinity, it is called as constant volume process, that is isochoric process. Therefore, any process can be expressed in terms of a generalized thermodynamic relation. It's easy to solve the energy interactions in a process, that is work transfer and heat transfer. Now coming to this polytropic process from 1 to 2, the P1 V1 whole power n is equal to P2 V2 whole power n, that is called as constant. Now the PdV work in a closed system can be calculated by the integral PdV from lower limit of V1 and upper limit of V2. In the PdV, P can be expressed in terms of volume from this generalized equation, that is P is equal to P1 V1 whole power n by V power n from this relation. The P1 V1 is constant, that's why it can be taken out. Now the integration becomes dV divided by V power n, that is equal to V power minus n plus 1 divided by minus n plus 1. After substituting this lower limit and upper limit and simplifying, plus n and minus n, here also plus n and minus n, the final equation for work is P1 V1 minus P2 V2 by n minus 1. Or it can be expressed in terms of temperature ratio also. The temperature ratio also has greater flexibility, can be converted into the pressure ratio or volume ratio. See, the T2 by T1 is equal to P2 by P1 whole power n minus 1 by n, or T2 by T1 is equal to V2 by V1 whole power 1 minus n. Coming to these energy interactions, after work, the heat can be calculated from the first law of thermodynamics. The Q is equal to W plus delta U. Substituting the expression for W and delta U is equal to mCV T1 minus T2 according to the same convention, minus m T1 minus T2 can be taken out. The rest of the terms are n r by n minus 1 and Cv. The Cv also can be expressed in terms of the gas constant, since there is a relation between the gas constant and Cv, that is the Cp minus Cv is equal to gas constant R. And also the second relation shows Cp by Cv is equal to gamma. Simplifying these relations, the difference and this ratio, finally the Cv is equal to R by gamma minus 1. This term is very similar to the first term, that is R by n minus 1. The second term now is R by gamma minus 1. Substituting this Cv in this expression and simplifying, this is a minus 1 and the plus 1, we got the first term is equal to work. The second term is a multiplication factor gamma minus n by gamma minus 1. Substituting this work W in place of the first term, the heat can be expressed in polytropic work into some multiplication gamma minus n by gamma minus 1, where n is changing from 0 to infinity. For example, if the n is equal to 0, this becomes the constant pressure process, and the Q is equal to W into gamma by gamma minus 1. The numerator is gamma 1.4, denominator is gamma minus 1, that is 0.4. Now see, since gamma is more than gamma minus 1, naturally the heat transfer is more than the work transfer in the constant pressure process. The additional energy supplied becomes to increase in the internal energy. Therefore, Q is equal to delta U plus W in a constant pressure process. In next case, If n is equal to 1, that is isothermal process. N is equal to 1 means the numerator is gamma minus 1, denominator is also gamma minus 1. Now this gets cancelled, the Q becomes W in isothermal process. In Q is equal to W means there is no change in internal energy. The difference, that is Q minus W, is 0. And also the temperature is constant, that's why the internal energy is also is constant in isothermal process. In the next case, N is equal to gamma. Here n is equal to gamma. After substituting n is equal to gamma, the numerator becomes gamma minus gamma, that becomes 0. That is Q becomes 0. Since W is not equal to 0, this becomes 0. The 0 into this one, Q becomes 0. The Q becomes 0 means this is called as adiabatic process. In the last case, n is equal to infinity, and this constant volume process. The PdV is equal to 0, there is no change in volume, means dV is 0, that's why W is equal to 0. And then the second term is equal to infinity, but not Q is not equal to 0. Thank you. A numerical problem is given to demonstrate the polytropic process in thermodynamics. Solve the polytropic process in air compression and expansion with the index values 0, 0.5, 1, 1.4, 2 and infinity. Consider the initial condition at 5 bar and 1 meter cube. The volume ratio in compression and expansion respectively are 0.5 and 2. Volume ratio means the ratio of higher volume to lower volume. At constant volume heat addition, that is compression, consider the final pressure as 25 bar. Similarly, at constant volume heat rejection, that is expansion, the final pressure is 1 bar. Analyze your result, find the work at each case. A computer code has been developed to demonstrate the nature of this process, thermodynamic process. Now see here, this is the compression process and this region is expansion process. In the compression process, the polytropic index is changed from 0 to infinity. This is 0, 0.5, 1, 1.4, 2, this one is infinity. Now this is the direction of increase in the polytropic index, value of polytropic index, and this is the direction of polytropic index. Now this in this expansion, n is equal to 0, n is equal to 0.5, it's 1, 1.4, 2 and this is infinity. Coming to the solution of this numerical problem, in the compression process, the volume ratio is considered as 0.5, that's why the final volume is 0.5 meter cube, whereas the initial volume is 1 meter cube. The first consider the constant pressure process where n is equal to 0. According to this thermodynamics, W can be calculated from P1 V1 minus P2 V2 by n minus 1. For the constant pressure process, the work is equal to P into V2 minus V1. After substituting these values, the work here is minus 250 kilojoules. So the minus is the compression process, the work done on the system, that's why the direction is negative. The heat is calculated from MR T1 minus T2 by n minus 1, gamma minus n by gamma minus n. Or this is W into gamma minus n into gamma minus 1, where n is equal to 0, that's why after substituting this value of work, the heat is minus 875 kilojoules, heat rejected from the system. The internal energy can be determined by algebraic sum of energy interactions or fundamental equation mCv T2 minus T1, that is equal to minus 625 kilojoules. The internal energy is decreased. For example, if the polytropic index n is equal to 0.5, the final pressure in the compression process can be calculated from P1 V1 whole power n is equal to P2 V2 whole power n. Therefore, P2 is equal to 707.1 kilopascal, whereas the at the inlet the initial pressure is 500 kilopascal. Similarly, the W can be calculated from this formulation: minus 292.82 kilojoules. The heat transfer is minus 659 kilojoules. The delta U, the change in entropy, is minus 366.1. For isothermal process, the PV is equal constant for the ideal gas, that is N is equal to 1. The work is calculated from the fundamental equation P1 V1 log P1 by P2 or V2 by V1, since P1 V1 is equal to P2 V2. Now the work is minus 346.57. The heat is minus 346.57. Both are same. Since gamma minus n by gamma minus 1 is getting cancelled, therefore the difference in the energy interactions is 0. The fourth case, adiabatic process, n is equal to gamma, that is 1.4. The final pressure is 1319.5 kilopascal. The work is minus 302.67 kilojoules. The heat is 0, since in the adiabatic process n is equal to gamma, that's why gamma minus gamma is equal to 0. The change in internal energy is equal to work according to the first law of thermodynamics. The change in internal energy now here it is coming positive 302.67. For next case, n is equal to, for example, this is a polytropic process. The final pressure is 2000 kilopascal. The work is minus 500 kilojoules. Q is 750 kilojoules. Delta U is 1250 kilojoules. The last case, that is n is equal to infinity, this becomes a constant volume or isoporic process. The constant volume means there is no change in volume, that is integral PdV is equal to 0. That's why work is 0. The Q is equal to U2 minus U1 from the first law of thermodynamics, that is 5000 kilojoules came. The change in entropy is also same 5000 kilojoules. Now the same formulations has explained and applied for the expansion process. In the expansion process, the final volume is double of the initial volume. If the initial volume is 1 meter cube, the final volume is 2 meter cube. Now let us consider the first case, that is a constant pressure or isobaric process, n is equal to 0. Now work is coming plus 500 kilojoules. The heat is 1750 kilojoules. Delta U, change in internal energy, is 1250 kilojoules. In the second case, polytropic process, where n is equal to 0.5. The final pressure is 535.35 kilopascal. The work is 414.21 kilojoules. The heat transfer is 932 kilojoules. The change in internal energy is 517.8 kilojoules. Whereas for isothermal process, that is n is equal to 1, the work is 346.57. Heat is same 346.57. The delta U is equal to 0, since there is no change in temperature. There is no change in internal energy. The fourth case is adiabatic expansion, where n is equal to gamma, that is 1.4. In this adiabatic expansion process, after expansion the pressure is decreased from 500 kilopascal to 189.46 kilopascal. The output, that is work from this expansion, is 302.67 kilojoules. The heat transfer is 0, as since it is a adiabatic process, it is fully insulated. The expansion process is fully insulated. Therefore, the change in internal energy is equal to the work. That is, work is 302.67. Change in internal is minus 302.67. The next case is polytropic process, where n is considered as 2. The final pressure is 125 kilopascal. After expansion, the work is 250 kilojoules. Heat transfer is minus 375 kilojoules, that is rejection. The change in internal energy is minus 625 kilojoules, that is internal energy is decreased due to heat rejection. The last case is volume isochoric process or constant volume process where n is equal to infinity. W is equal to 0 in constant volume process. The heat transfer is equal to minus 1000 kilojoules. The change in entrance is also equal to minus 1000 kilojoules since there is no any work interactions. So the summary of this all this process, that is the compression process and expansion process, shows with the x-axis is the volume and the y-axis is the pressure. The polytropic index is changed from 0 to infinity. See, the first case is n is equal to 0, that is constant volume process. N is equal to 0.5, the polytropic process. N is equal to 1 is isothermal process. N is equal to 1.4 is adiabatic process. N is equal to is also one form of polytropic process. N is equal to infinity is a constant volume process. These are the observations, the change in volume, and this is a increase in the pressure ratio. Whereas here the expansion, the increase in the pressure is less compared to this compression process. And also there is a difference between this area under PV diagram. Area under PV diagram is called as work transfer. This area is different compared to this area. This is a steep, the slope is also more. The conclusion of this observations from this numerical problem, and the tabular form is prepared for both the compression process as well as the expansion process with the change in the polytropic index from 0 to infinity. The work is negative in the compression process as work done on the system. The heat is rejected from n is equal to 0 to till here, that is n is equal to 1. In the adiabatic process, the heat is 0. The heat is positive for polytropic process where n is greater than gamma, and also constant volume process. Here the heat rejected from the system, your heat is supplied to the system. The last one is internal energy is decreasing in the first two cases. There is no change in internal energy for isothermal process as it is discussed, and internal energy is decreasing for adiabatic process, polytropic process where n is more than gamma, and also constant volume process. And see, these are the results for expansion process with the same change in polytropic index. In the expansion process, we know the work done by the system, that's why all the works are positive. Whereas in constant volume, there is no change in volume, that's why work is 0. For the initial process, that is n is equal to 0, 0.5, 1, the heat is positive, that is work, the heat is supplied to the system. There is no heat for adiabatic process. The heat is negative for polytropic process n greater than gamma, and n is equal to infinity. Here, compared to this compression, the reverse results are coming. The internal energy is increasing for first process, second process. There is no change in internal energy for isothermal process. The internal energy is decreasing for this last three process, that is adiabatic process, polytropic process, n is greater than gamma, and constant volume process. The summary of these results shows the slope of curve in compression is much more than the expansion process. It shows the pressure rise with a small volume change in compression and minor pressure change with a large volume change in the expansion. It also shows that the size of turbine is bigger than this compressor at the same pressure ratio. The table 1, table 2 shows the energy interactions in the compression as well as the expansion respectively. In the compression region, the work is increased from and finally 0, which is change in polytropic index from 0 to infinity. The work in isothermal compression is less than this adiabatic process. That's why mostly the design engineers prefers isothermal compression process. But practically it is difficult. That's why they will use the intercoolers between the multi-stage compressors. In compression, the heat is negative with n is less than gamma, and positive with n is greater than gamma. Thank you.